we'll have London dispersion forces. Everything, yes, correct. Excellent. How to do the Vesper model project. Okay, give me just a second and I'll go over that. Yes, that's correct, Hunter. All right. So somebody wanted to know how to do the Vesper project. So I'll go over that really quick. Okay, so in your textbook, I think it's what? Yes, there is information on the project on the assignments tab. So in the textbook, in like section 5.2, there's a table. I think it's table 5.1. It's got all the different structures, like tetrahedral, bent, trigonal planar, octahedral, seesaw, T-shape, all that kind of stuff. You're not stupid. And then you're just going to make a model out of it. But if you give me a couple minutes, when we get to the end of class, I'll just kind of go over the Vesper model project. All right. So let's do London dispersion forces. All right, so everything has them. They kind of remind me a little bit of static electricity, kind of. If you have a balloon and you rub it in your hair and then you put it near the wall, a lot of times it'll stick to the wall. It sticks to the wall because of static electricity. So what happens is you have this balloon and you've rubbed it in your hair and you've either rubbed electrons onto it or off of it. So you get all these negative charges on the outside of the balloon and you put it near a wall. Now the wall was neutral before, so it was pluses and minuses all the way down. So it starts off looking kind of like this, or like that. But when you put the balloon near it, all the negative charges kind of run away, right? So then what you're left near the balloon is a bunch of positive charges, and that's what sticks it to the wall, is the electrons and the sticking to the positive charges, so the protons of the other atoms. And London dispersion forces are pretty similar in that you have one atom and you have another atom and they have a positive nucleus. And let's say we're just looking at hydrogen, all right? So you start off like this. So the electrons are in those two spots. And as you bring them close together, one of the electrons is kind of scoot to the back. So let's say it's this one. So then the electron comes here. Then this will be attracted to the nucleus and it'll temporarily have a dipole moment. So if you look at it, you see that one part is negative and one part is positive. So you've got a dipole moment like this, it's temporary, and then another one like that. Now, in a minute, what's going to happen is this guy's going to go back around to the front, and then this one's going to go to the back. So it switches back and forth and back and forth and back and forth. And in one of the tutorials that I've got on the homework document, there's, can't think of the word I'm trying to say. An example, because that's a good enough word. They wouldn't cancel out. You would think they would. But this is the nucleus, and this is on the outside of the nucleus. So even though the negative charge is attracted to the nucleus of the other atom, it's not going to fall into the nucleus of the other atom. It has to do with quantum mechanics there, because your energy level has to be at least 1. And so that means it has to be 1 one distance away from the nucleus. So as close as the electron could get would be one energy level away from the other nucleus, even if it transferred to the other atom, which it won't transfer to the other atom, but that's a good question. But that's why they don't cancel out, is quantum. So let's take a look at the things that will increase and the things that will decrease London dispersion forces. All right, so there are two things that will increase it, and that's the molar mass and what I'm going to call stackability. And I'll show you what I mean by that. So let's say we have a molecule like this. Oops, I didn't know what that was all about. Okay, so you've got a molecule that looks like this. And then you have a molecule that looks like that. The one on the right is bigger. So if you put it next to another one, there's going to be a lot more surface interaction there than there would be with the small one, just because it's smaller. So this one would have more London forces because it's larger. And the other thing that affects it is the stackability. One thing that I thought was hysterical that they put in the homework that I was looking at, I think I was looking at it yesterday, was it gave you stuff that looked like this. Like that. And they didn't explain the parentheses there. Sure, no problem. So London forces are when you have two atoms, they can be any two atoms, and you bring them close together. All atoms have a positive nucleus, and they have electrons on the outside. So let's say in one moment, this atom has an electron and it's on the right. It's going to cause the electron on the other one to also scoot to the other side so that they decrease electron repulsion. So temporarily, that's going to be attracted to it. Now, in a moment or two, this one will change places, and so it'll look more like this. And then this one will be attracted to that. So it goes back and forth, which is why they call it a temporary dipole. Sometimes you may even see the pictures drawn kind of like this. You've got like an atom, and then they kind of draw it almost moon-like. And they say like there's the, and then you see how there's not a lot of electron density on the one on the left there. It looks like Pac-Man. So you'll see it drawn both ways sometimes. All right, so back to this one up here. This one has a branch. I could tell it's a branch because it's in parentheses. There are two times they put these things in parentheses. So let me show you the two things they might do it for. Let's say you had something like this. All right. So the things on the ends are always CH3 because the carbon here and the carbon here are only bonded to one thing. So they need to have 8 electrons around them, so they would look like this, right? And the ones in the middle would be like this because they're attracted to, not attracted to, they're attached to two different things. So you can write the whole thing out, which would be CH3, CH2, 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 CH3, or you can shortcut it by going CH3, CH2. And then count up how many of them there are. So there's 1, 2, 3, 4, 5 of those. So 5 on how many CH2s there are. And then it ends in this CH3 here, so we just tack that on to the end. And that's really nice, especially when you get something that's got like 20 CH2s in the middle. It's just a lot quicker to write it like this. In this case, I know it's a straight chain because it's CH2. If it's CH2, it's not kind of branching off anywhere. There are other times I can see it look like this: CH3, CH2, CH2, parentheses CH3, and then CH3 again. And what that's saying is that you have, let's see, 1, 2, 3, 4 carbons in a row. Right? And then on the 1, 2, 3, on the third one from the left, so that's 1 here, 2 here, 3 here, you have another CH3. So this would be the CH3 that's added. So you got C, 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 C. And then on this one, you've got another C. Those all have H's. Actually, this one should just be CH. All right. So if you see parentheses and you see the CH2, it's just telling you it's a straight chain, but there are so many CH2s they didn't want to write it. But if you see something that either has a CH3 in it or ends in a CH3 or is like an oxygen or nitrogen, it's telling you it has some sort of a like a branch growing off of the carbons. So I'm going to give you an example to give it a try. That's a good question. The one on the end has 3 H's, because if you take a look at this one right here, oh, I see what you're saying. This one should have an H. Is that what you were asking about, Jackson? Okay, yeah. It's supposed to have CH3. I just missed one. Sorry about that. All right, so let me give you an example. No problem. Do this one. I'll give you 2 of them. Draw that one, and draw this one. Oops, I'm giving you the answer. Let me do that again. I'll change it. You know what? I can't even read this at this point. How many CH2s did I have on that structure just a second ago? Anybody remember? 3? Okay. Thank you. All right. Okay, so draw those 2. I'll give you about, I don't know, about a minute or 2. So when you either get to the point that you're stumped and can go no further, or you get finished with it, just put a D in the chat for done. Oh, I didn't get to the stackability part yet. So I wanted to show you this first, and then I'm going to show you about stackability. Yeah, no, you didn't miss anything. All right. Anybody else done? All right, I'll give you about 1 more minute. No problem, I'm going to show you how to draw them in just 1 second. That's okay. All right, so I am going to show you how to draw them. So this one, we've got the parentheses here, and it's telling me how many of them there are, and it's got a CH2, and there's no CH3 inside the parentheses anywhere, and it's not like an oxygen or nitrogen or something, and that tells me that it's just going to be a straight chain. So that's what that would turn into. If you wanted to draw the skeletal structure that's just the sticks, let's see, 1, 2, 3, 4, 5 carbons. So starting here, that's 1, 2, 3, 4, 5. All right, and so let's take a look at the one at the bottom. The one at the bottom has parentheses right here, and there's no number on the outside, and it's CH3, and what that's telling me is that this has to be a branch. If it ends or has a CH3 inside the brackets anywhere, or it's an oxygen or nitrogen or something, that's saying that it's a branch. So it would look like this. And it doesn't really matter if you put the CH3 on top or if you put it underneath, just either way. All right. I'm not going to ask you to draw the skeletal structure for them, but it might ask you something like which of the following has more London forces, and so the ones without branches are more stackable, so they would have more London forces. So the main thing I just wanted to show you was that if you see something in parentheses, most of the time it's indicating a branch. Well, I wouldn't say. A lot of the time it's indicating a branch. So you see how this is kind of sticking off of that carbon there? Mm-hmm. This one, you can tell it's not a branch by 2 things. One is they have a 3 outside telling you that there are 3 of those. And the other thing is on the inside, they're all CH2s. So there aren't CH3s. It's not an oxygen or nitrogen. Yes, correct. This is drawing organic structures or drawing hydrocarbons. There's a little bit of it in, it's either section 6.2 or 6.3, I don't remember, but it goes into a lot more detail in chapter 19. But I also wrote out the some stuff on the homework help pages as well. Absolutely. Okay, so the stick version of this one, let's see, there's 1, 2, 3, 4, 5 carbons in a row. There's going to be 1, 2, 3, 4, 5. On the 4th one from the left, which would be this carbon here, has So that's what it looks like with the branch on it. Correct. CH2 is not a branch. Now you might see a branch that's CH2, CH3, but because you see the CH3 there, you know that that whole thing is a branch, that it would just go CH2, CH3. All right, anybody need a second on this page? No? Okay. All right, so let's take a look at the stackability of these things. So let's say we have this and this. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. Okay. So for the structures, how do you figure out the number of carbons? You mean the stick ones? Okay, I'll show you how to figure that out. Give me 1 second. Let me finish this, and I will show you how to do that. All right. So this one would be a CH3. All right, so that's basically a chain. And then this one would look like this. This is an H. Okay. So let's put them in stick structure because that gives you a better idea of the stackability of them. So the one on the left has 6 carbons. So to draw the stick structure, every time I see a point, that means there's a carbon. So since there are 6 of them, 1, 2, 3, 4, 5, 6, then I'm going to need to have 6 points. So this is 1, 2, 3, 4, 5, 6. Right. Now let's take a look at the other one. It's got 1, 2, 3, 4 in a row. We'll get to the other 2 in a second. So we got 1, 2, 3, 4. And then looking at these on the third carbon from the left, which is this one right here, from that one we have 2 more carbons that go up from there. So they could literally go up or they could go down. It doesn't really matter which way you draw it right now. So this would be 1, 2, like that. Now if I draw another one like this, compared to another one like this, which set do you think is going to stack better? Set A or set B? Set A, because there's not that branch in the way. Sometimes they call those branches, they'll call them steric interference, not the branch itself, but they're causing what's called steric interference, which just means there's something in the way so it doesn't stack well. It's things that are too close together, basically. So this one would have more London forces because the more surface area of the molecules you have touching, the more London forces there are. All right. So did you see how to do those carbons, Chad, when I drew those out a second ago? Okay, cool. All right, so let's take a look at a couple of different, a couple of other forces that we have. So we have dipole-dipole. Then we have hydrogen bonding. And we have ion dipole. So dipole just means you have polar molecules and they're orienting each other based on their polarity. So if I had HCl, like this, this is going to be partially positive, this is going to be partially negative. And so if I have a lot of these together, then all of the H's are going to be pointing closer to the Cl's because the H's are partially positive and the Cl's are partially negative. So these two things here are going to be attracted to each other, not attached to each other, just attracted to each other. So that's called dipole because you have one polar thing here and another polar thing there, and the polar things are attracted to each other. You could have it like this, or you could have two different polar molecules. You could have HCl and HF, or let's see, H2S, or something like that. So a bunch of different kinds you can have. Now with hydrogen bonding, so London forces are the weakest, then dipole forces, then hydrogen bonding is stronger than that, and then you have the ion dipole forces. So hydrogen bonding is inside your molecule. You should have a hydrogen connected to either a nitrogen, an oxygen, or a fluorine. And if you see that, then you know you have hydrogen bonding. For example, with water, you have the HO. So that's going to tell me that I'm going to have hydrogen bonding when I have water. And all that means is that the hydrogen of one is going to be attracted to the oxygen of the other, like that. So this hydrogen is going to be attracted to this oxygen because it has all these lone pair electrons on it. Right? Now the water has three different kinds of forces. The dipole has two forces. That would be the London dispersion forces and dipole. The water has the London dispersion forces, the dipole, and it has hydrogen bonding. Because both the water is polar and it has hydrogen bonding and it's a molecule, so it has London dispersion forces. And then if you have ion dipole, it's kind of like when you dissolve salt in water. So you'll have some sodium ions and some chlorine ions. And then you have water. So they're going to be surrounded so that the positive ion is going to be attracted to the negative of whatever has the dipole. So in this case, our polar molecule is water. So you've got ion dipole. So it's referring to the two different kinds of compounds you've got there. And I believe the ion dipole is the strongest because you've got an ion. Let me see what else I want to go over. We'll make sure I don't miss anything. Let's see. Okay, let's see. Sure. That's a good question. I'll show you that one, Chad. And Josh? All right. So let's take a look at the ion dipole. No, that's okay. All right. So with the ion dipole, what you have is you have an ionic compound, and then you have some sort of polar compound. Let's say in this case we have H2S. All right. We could have H2S, H2O. We could have HCl. There are all kinds of stuff that. So sodium chloride, when it dissolves into ions, will fall apart into sodium plus and Cl minus. And that's because it's ionic. So with ionic, they're close to each other, but they're not sharing electrons because one atom got the electron from the other one. So in this case, the sodium has given chlorine the other electron. So when you put them in water or something, they'll separate out. So H2S is going to stay together because it's a covalent compound, not ionic. So it's not going to fall apart like that. All right, so this part is partially positive. This part is partially negative. So if you're guessing, looking at the H2S, will the H or the S be more attracted to the Cl minus? The H. Correct. Because the H's are positive and Cl minuses are negative. So what's going to be attracted to the sodium then? The S. Very good. All right. So because what you want to have is a plus and a minus, that's what's going to be attracted to each other. So how do I know which end of the H2S is plus and which end is minus? Dipole electronegativity? Yes, that's correct. The one here that's more electronegative is sulfur, so that's why it gets the partial minus. And then hydrogen is less electronegative, so it gets partial positive. Let's say I had SF2. If I had that, something like this, with all the lone pairs and whatnots. All right, so which one is going to get perfect? That's just what I was going to ask. I'm going to say which one is the minus part now, and the one that's more electronegative is the fluorine. So this time that's going to get the partial negative, and this is going to get the partial positive. So you're just looking for which one is more electronegative, and that gets the partial negative part. So when you put these things together, let's say we have liquid H2S, and we put it in a beaker, and in the beaker we pour some we pour some sodium chloride into it, and we stir it so that the sodium chloride dissolves. What's happening is the sodium and the chlorine will get slightly separated so that you get some H2S's in between there. So this is going to have the S's near it. And this is going to have the H's near it. We're sort of getting a little jumbled there toward the middle. But so what we've got the positive being attracted to the negative end. and the negative being attracted to the positive end. Because we have a polar molecule, which is H2S, and an ionic compound, they call that an ion dipole. Yes, that is correct. Cl would be attracted to H. And part of the purpose of learning these intermolecular forces is to be able to predict boiling points. Let's take a look at the things that make boiling point increase. We've got 7 minutes, that ought to be plenty of time. All right, so we're looking at boiling point. So you have a liquid, and it's being heated. This is my idea of heat down here. Okay, and then to get it to boil, it's got to turn into a gas. Are the atoms closer together in a liquid or a gas? In the liquid. So in order to turn it into a gas, I have to break some of those intermolecular forces. So let's say I have something that has London forces and something that has ion dipole forces. Which one do you think is going to have the higher boiling point? This one, because this is a stronger, it's a stronger bond. What about dipole-dipole? And hydrogen bonding? Yes, the hydrogen bonding is stronger. So it's going to have the higher boiling point. Now, sometimes they want to compare things that just have the same kind, like something that has London dispersion forces and something else with London dispersion forces. In that case, you're going to look at two things. You're going to look at the size of the two compounds, and the one that's bigger has more surface area, so it's going to have more London forces. So if it's big, it's going to have the higher boiling point. And then if we were looking at it again and we had something that was branched and something that's not, the one that's not branched has the higher boiling point. It wouldn't necessarily mean higher polarity, because you could actually have something with lots of surface area that's not polar at all. But more surface area means you have more of those atoms that are doing that temporary dipole thing. And the more of them you have doing that, the stronger the hold is going to be between the two of them. It's almost like Velcro, kind of holding them together. And the more hooks you have in the Velcro, the stronger it is. So let's say I have like a piece of Velcro like this, and I have one bit of fuzz and one hook, or I have some Velcro like this, and I have a whole bunch of fuzz on the fuzzy end, and then a whole bunch of hooks. The one with more hooks is going to be held together more tightly. And then you can look at dipole-dipole. If you have HCl, HF, let me see. We already talked about that. We kind of went over this already. So let's say we're looking at London dispersion forces and we're looking at, molecules like that compared to molecules like that. Obviously, this is going to have a higher boiling point because it's bigger. But let's say we're looking at something like Cl2. So that's chlorine and chlorine. That's also going to be just London dispersion forces because it's a nonpolar molecule. Cl2 is nonpolar. We're comparing that to Br2 and I2. As they get bigger and bigger and bigger, the larger ones are going to have a higher boiling point. The reason is because the electrons, I'm just going to sound a little weird the way I describe it, but when you have something that has lots of electrons on it, so as you go further and further down the periodic table toward the bottom, they get so many layers of electrons, and they're so far from the nucleus, they get kind of squashy, meaning they're more easily. Am I going in and out? Okay. Give me 1 second. Any better? Okay. Boiling point. Oops. What did I do there? Oh. And does it sound any better? Okay. All right. All right. A BP stands for boiling point. So the more squishy they are, the more polarizable they are. If they're very polarizable, then that means they can be held together better. Ari, what's your question?
Professor, your voice is cutting.
Again, still, okay. Let me see if I can fix that. One second. Let me pull this up here. All right. Any better yet? Still the same. Okay. And let's right. It's 11 o'clock, so to go working on your homework. Go through the weeks so you don't stuck at the top of it. All right. Take a look at homework documents because there's a lot of good information that you're going to need. So even if you think you did, please scroll through to see if there's anything like, oh, no. Okay? All right. I will see you guys on Wednesday. You're welcome. You